Hello guys, so in today's video we're going to go over row echelon form and also reduce row echelon form. All the text and examples I'm using in this video are from this book, Linear Algebra and Its Applications, 5th edition, David C. Lay, Stephen R. Lay and Judy J. McDonald. So you can check out the book as well. It's quite good. So let's start. A rectangular matrix is in echelon form or row echelon form if it has the following three properties. So a rectangular matrix is something like this. uh, it has like here it has four columns and three rows. So the properties are all non-zero rows are above any rows of all zeros. Each leading entry of a row is in a column to the right of the leading entry of the row above it. All entries in a column below a leading entry are zeros. I'll go over this part and then I'll explain each and everything. If a matrix is in echelon form, it satisfies the following additional conditions. Okay, sorry, if a matrix is in echelon form, satisfies the following additional conditions, then it is in reduced echelon form. So the leading entry is each non-zero in non-zero row is 1. Each leading one is the only non-zero entry in its column. So like let's see this example first. This is a reduced echelon form. So let's see the first property. All non-zero rows are above any rows of all zeros. So like this is a non-zero row, and if there was a row of all zeros, then it would have been above it. In this example we don't have something like this. Each leading entry of a row is in a column to the right of the leading entry of the row above it. So here 2 is the leading entry, it's to the right, sorry, and 1 is the leading entry for the second row. So 1 is in a column to the right. Here 5 by 2 is the leading entry and it is still in a column to the right of 1. It doesn't matter how many columns, it only matters is it is to a column of to the right. So if this is to the right of this and the last one is to the right of the second last one, then you can see you get a step like pattern where something of this sort is formed, where the zeros form some sort of steps. All entries in a column below a leading entry are zeros. Yeah, so this means that for this row this 2 is the leading entry and all entries below it are 0. 1 is the leading entry and 0 is 0 of course below it. And now let's have a look at this. This is actually a reduced row echelon form. So the properties, again we'll check all of them. There is no completely zero row, so we don't have to check for that. Each leading entry of a row is in a column to the right of the leading entry of the row above it. So 1 is to the right of this one and this one is to the right of this one. So again you can see these are the leading entries. The leading entry, if you're not sure what that is, so leading entry is the first non-zero element in a row. So 1 is the leading entry here, this one is the leading entry here, this one is the leading entry here, this 5 by 2 was the leading entry. And so you can see that it's to the right like this, and all entries in a column below leading entry are zeros. So this leading entry has only zeros, this leading entry only has 0, and this leading entry does not of course have anything below it. Okay, so now let's have a look at this. An echelon matrix, respectively reduced echelon matrix, is one that is sorry, I missed these 2 points. The leading entry in each non-zero row is 1. So for the reduced echelon form, this entry has to be 1 for a non-zero row. Here it could have been anything, but here it has to be 1. And each leading one is the only non-zero entry in its column. So for instance, this is the leading one and it is the only non-zero entry in its column. Okay. An echelon matrix, respectively reduced echelon matrix, is one that is in echelon form, or respectively reduced echelon form. Property 2 says that the leading entries form an echelon step-like pattern that moves down and to the right through the matrix. So you can see this is sort of a step-like pattern. If you had more entries like in these examples, you get a step-like pattern. And property 3 is a simple consequence of property 2, of course, but we include it for special emphasis. So if this holds true, then this of course holds true, and but we still take that. Now we have an example. I've taken this snap from the book. So in these examples, these black squares may have non-zero values and these starred entries may have any values. So for this matrix, which is in echelon form, you can see this is the leading entry, this is the leading entry, this is to the right, and these stars can have any value. It can be 0 as well. So now you might wonder what would happen if this was 0. Then this would no longer have been the leading entry, because if this was 0, then if we would have selected the next non-zero value. In this example as well, you can see this is the leading entry, this is the leading entry, the first non-zero entries, and then the rest values can be anything including 0. These two matrices are reduced echelon in reduced echelon form because the leading entries are 1. So like here we had this square, black square, which denoted any value including 1. Here we are specifically dealing with 1. So this is 1, these are 1s, and these values are anything. But you might be noticing something interesting. Why are there no stars here? Right? You might question this. Why are these specifically zeros? Then we go back to this property. Each leading one is the only non-zero entry in its column. This wouldn't have made much sense here, but as you can see in here also, this one was the only non-zero entry. This was the leading one, this was the leading one, the rest everything was 0. So for reduced row echelon form, this is 1 and everything else in that column is 0. Okay, I hope that makes it clear. Any non-zero matrix may be row reduced, that is, transformed by elementary row operations into more than one matrix in echelon form using different sequences of row operations. Makes sense. However, the reduced echelon form one obtains from a matrix is unique. So like they're saying that you can take any non-zero matrix and use elementary row operations and convert it into multiple matrices which are in echelon form, and then use different sequences of row operations using however, if you get the reduced echelon form, then it is unique for any matrix. So if a matrix is row equivalent to a echelon matrix U, we call U an echelon form of A. Makes sense? If U is in reduced echelon form, we call U the reduced echelon form of A again. And now this is something, if you're using calculators and stuff, they use the abbreviation RREF for reduced row echelon and REF for row echelon. So we are done with that part. Now let's have a look at what are pivot positions. This is also quite important. So when row operations on a matrix produce an echelon form, further row operations to obtain the reduced echelon form do not change the positions of the leading entries. I'll explain this. Since the reduced echelon form is unique, the leading entries are always in the same positions in any echelon form obtained from a given matrix. These leading entries correspond to leading ones in the reduced echelon form. Okay, so let's break it down. When row operations on a matrix produce an echelon form, so like you get an echelon form finally, further row operations to obtain the reduced echelon form do not change the position of the leading entries. So like if you had gotten this matrix and you wanted to now get the reduced row echelon form, this wouldn't make this vanish from here and the first non-zero entry going here. This wouldn't happen. The reduced row echelon form would also have the one here itself. And since the reduced row echelon form is unique, which we had discussed in this theorem, sort that leading entries are always in the same position in any echelon form obtained from a given matrix. So we saw that one matrix can have multiple echelon forms, but the leading entries will always be in the same position. So like there might be a 2 here, there might be a 5 here, there might be a 7 here, but they will always be in these two positions, the first non-zero elements. Since the reduce these leading entries correspond to leading ones in the reduced echelon form. Again, in the reduced echelon form, these are now ones. A pivot position in a matrix A is a location in A that corresponds to a leading one in the reduced echelon form of A. Okay. A pivot position in a matrix A is a location in A that corresponds to a leading one in the reduced echelon form of A. A pivot column is a column of A that contains a pivot position. Let's understand these by the above examples first. So a pivot position in a matrix A is a location in A. So let's say this is our matrix A. that corresponds to a leading one in the reduced echelon form of A. So let's say you can see this is what would the reduced echelon form of this matrix look like. So this is the position of the leading one of the reduced echelon matrix. So this is the pivot position in this matrix as well. So theoretically, if you have a row echelon matrix and you need to find the pivot positions, you just need to think what would have been the position of the leading one in the row reduced echelon matrix. So this one would have been here, right? So this is the pivot position for this row. This one would have been here, right? So this is the pivot position. This one would have been here similarly. So this is the pivot position. This is also the pivot position for this matrix. This is the pivot position for this row of this matrix. Similarly, this one and this, these are both pivot positions for the respective matrices. Hope that makes sense. So now that we have gone over both of these, we are going to finally look at this example. Row reduce the matrix A below to echelon form and locate the pivot columns of A. Oh yeah, we forgot to discuss A. A pivot column is a column of A that contains a pivot position. Nothing special. So this is a pivot point. So this column is a pivot column. This is a pivot point. So this column is also a pivot column. All this text has been taken from the book. So you can just read. It's in the second chapter, I believe. So now example 2. Row reduce the matrix A below to echelon form and locate the pivot columns of A. Okay, so we have this matrix right here. You can see right now it is not in echelon form. Why? Because first of all, there needs to be a 0 here, and then some values might start from here, because below, let's look at the properties once again. All non-zero, each leading entry of a row in a column is to the right of the leading entry of the row above it. Yeah, so this point is, we'll just use this point, we won't check for the third again and again. So this is the leading entry here, and this leading entry is to the left right now. It needs to be to the right, so it needs to be like here or somewhere beyond that. So let's use a basic strategy. The top leftmost non-zero column is the first pivot position. um, the top of the leftmost non-zero, leftmost, so this non-zero column is the first pivot position. Yeah, a non-zero entry or pivot must be placed in this position. Okay, a good choice is to interchange rows 1 and 4, because the mental computation in the next step will not involve fractions. They're just doing this. You can do this by any way, but we're going to just look at the way they did this. So they interchange these two rows. You can do this. This is a valid operation. Now we need to create zeros below the pivot 1 by adding multiples of the first row to the rows below and obtain matrix 1 below. So let's see. They added this row. Let's see what they did really. So it seems they uh, added this directly. So you can see 1 plus minus 1 gave them 0, 4 plus minus 2 gave them 2, 5 plus minus 1 gave them 4, minus 9 plus 3 is minus 6, minus 7 plus 1 is also minus 6. For this, they had to multiply it by 2 and then add. So 4 into 2, 8, minus 3, 5, 5 into 2, 10, minus nothing. So again, it's you did not add or subtract anything, so you get 10, minus 9 into 2, minus 18, and then you add 3, so you get minus 15, minus 7 into 2, minus 14, and then you add minus 1, so you get minus 15. For the first one it was 1 into 2, and then you add minus 2, so you get 0. For the fourth column we haven't done anything yet. So the pivot position in the second row must be as far left as possible, namely in the second column. Okay, choose the 2 in this position as the next pivot. Okay, so we will now try to make this the pivot point. And now what we can do is add minus 5 by 2 times row 3. You might be wondering, why aren't we using row 1? Because if we use row 1, then we'll make changes to this 0, and we don't want that. We want this to stay as a 0. So when we add minus 5 by 2 times row 2 to row 3, let's just see what happens. 5 by 2 times this is minus 5 by 2 times. Row 3 is, this would become minus 5 by 2 into 5 minus 2, so this would become 0. 10 into minus 5 by 2, 10 into, yeah, sorry, I'm doing it the opposite way here. We need to do minus 5 by 2 times row 2 to row 3. So minus 5 by 2 times 4 is here 10. So once we add that, we get 0. Similarly, you can do the computations yourself. You see we get an entirely 0 row. And similarly, we did 3 by 2 times row 2 to row 4, and we got this, my only this column. So the matrix in 2 is different. Okay, there is no way to create a leading entry in column 3. Yep, we don't have a leading entry here. It's entirely 0. We can't use row 1 because that would destroy the echelon arrangement. However, we still have one thing. You might be losing hope, but don't. You can just exchange these rows, right? That is also a valid operation. And then what would happen? You'll get this column, and in this column you can see this is the I'll mark the leading entries now. First of all, you exchange these two columns, so now these are the leading entries: this one, this 2, this minus 5. This row does not have a leading entry because it is all zeros. So you can see this 1 is now the pivot, this 2 is now the pivot, this minus 5 is now the pivot, and these are the pivot columns. So this column and this column are the pivot columns. And if you look at the general form for this specific matrix, you can see this is a pivot position, this is a pivot position, and this is a pivot position. Rest all can take any values, and you 0 not restricted because it was a 0 here, but it is a star here, so any value. And then the matrix is in echelon form, we can see, and thus reveals that column 1, 2, and 4 of A are pivot columns. Again, a pivot, as illustrated in example 2, is a non-zero number in a pivot position that is used to create zeros via row operation. Yeah, the pivot in example 2 were 1, 2, and minus 5, 1, 2, and minus 5. Notice that these numbers are not the same as the actual elements of A in the highlighted pivot position shown in 3. So yeah, this was the original A matrix. So this one is now in the position of 0. This 2 is at the position of earlier minus 2, and this minus 5 is in the position of what was 3 earlier. So these are the pivot positions and these are the pivot columns. So I hope this made sense. I'll probably make a few more on some other elementary row operations and stuff, but this was basically focused on row echelon form and how to find out what are the pivots and stuff. So thank you.